This is the second video in the series Polarity of Molecules. It is titled Polarity of Molecules, Specific Molecular Geometries. As mentioned in the first video of the series, we will look at 5 specific geometries: linear, trigonal planar, trigonal pyramidal, bent, and tetrahedral. There are more complex geometries than this, and you might explore these in later classes. Here we will explore how specific geometry of a molecule can affect its polarity. We will look at specific examples of each of these 5 geometries. Again, the transitions here may seem a little odd within the video because it was originally a longer video. Welcome to Polarity of Molecules, Part 4. Now we're going to start looking at the individual geometries and how they play out with both polar examples and nonpolar examples of molecules. So we have 2 examples here. One is carbon dioxide, and I have a little model of that here. The carbon is a central atom, and it's bonded to 2 oxygen atoms. And unfortunately, I do not have a model of my other example, which is hydrogen cyanide. It has the same carbon central atom, but the terminal atoms are hydrogen on one side and nitrogen on the other. And we will see this difference in symmetry will make a difference in the polarity. Both are bonded in a straight line, making them have a linear geometry. So let's look at our carbon dioxide first. It has a carbon atom bonded to 2 oxygen atoms on either side. The oxygen atoms have the same electronegativity, the 3.5. And again, this came off the electronegativity chart, which is significantly different than our carbon. But notice the arrangement here. They are oriented exactly 180 degrees away from one another. So while, yes, we do have these concentrations of electrons, pulling those electrons away from the carbon, notice they kind of pull in opposite directions, exactly opposite directions. And I'm going to use this analogy a lot. It's almost like the electron or electronegativity tug of war. And in this case, neither side wins the tug of war because they're exactly opposite and they have exactly the same pull due to the symmetry. So this molecule does not have a separation of charge. Think of it, if you're a big mathematician, of vectors canceling each other out. So carbon dioxide is nonpolar. But let's look at hydrogen cyanide. Again, we have the carbon central atom. But now look, we don't have that symmetry of 2 oxygens on either side. In fact, we have a hydrogen, very low electronegativity, and then a nitrogen, which has a much higher electronegativity. And as you can see here, this nitrogen will start to pull those electrons that are involved in the bond towards itself, creating that separation of charge. So even though they're in the same line, this lack of symmetry helps us create a polar molecule because now we have a separation of charge. Here we have seen that geometry plays a role in polarity, and also symmetry plays a role in polarity. So linear molecules can either be nonpolar or polar, depending upon the atoms involved. Welcome to Polarity of Molecules, Part 5. Now we'll be looking at molecules that exhibit trigonal planar geometry. There's a central atom with 3 terminal atoms bonded around it. They all lie in one plane, and they are, if you can see here on this basic drawing, they're all about 120 degrees in angle apart from one another. Basically, this molecule lies flat. You could almost look at it like a 2-dimensional molecule. They're all in the same plane. I do have a model for one of them, but I don't have a model for the other molecule example. So my first example is boron trifluoride, which is I do have a model for here. And I have a representation of the electronegativities. As you see here, very similar to CO2 or carbon dioxide, these have a difference in electronegativities, but because of the symmetry, these, and if we go back to our analogy of an electron tug of war, nobody wins the tug of war. There's no side that wins the tug of war. All of the poles are exactly equal. So, and again, if you're a mathematician, you like vectors, the vectors cancel each other out. So as a result, there's no separation of charge. Boron trifluoride, and yes, this is a real molecule, is a non-polar molecule. So what happens if I happen to play God and take off a fluorine and instead, with my example 2, difluoroborane, I add a hydrogen instead of a fluorine? Does that change the picture? Well, it does a lot. The geometry is the same, but notice the symmetry is different. I have a hydrogen here as opposed to a fluorine. So this is much less electronegative. So the pull on the electrons is not nearly as great. The fluorines will kind of hog those electrons, pulling them up towards themselves. And here with difluoroborane, you see there is a separation of charge. These electrons are concentrated up here, creating a partial negative side and then a partial positive side down here. So difluoroborane, closely related to boron trifluoride, is polar, whereas the boron trifluoride is not polar. Separation of charge, and here we have no separation of charge. The charge separation cancels each other out. So symmetry plays a big role here. Trigonal planar molecules can either be nonpolar or polar. Welcome to part 6 of Polarity of Molecules. Now we will be looking at a new geometry, trigonal pyramidal. This is very similar to trigonal planar. However, if you notice with our model and also with the drawing, the 3 terminal atoms are pushed down and out of the plane with the central atom. So they're not all lying in the same plane. So what causes that push? What creates this type of geometry? Well, if you notice here in our drawing, these 2 little dots are our lone electron pair. And also in my model here, I've created a kind of a purple lone electron pair model. So this lone electron pair exerts a force, even though we don't see it in terms of a bond, it exerts a force on those terminal atoms and pushes them out of the plane. Well, now the question becomes, does this make a difference in the polarity? Remember, all our terminal atoms might be the same. So our first example, our only example, is going to be nitrogen trihydride. And again, this is the model also for nitrogen trihydride. You guys might know it by its common name, ammonia. It has 3 hydrogens as terminal atoms and a nitrogen as the central atom, and then our lone electron pair. So our hydrogen atoms all have the same electronegativity. However, because they're pushed out of the plane with the nitrogen, there is a side, a bottom side and a top side to our trigonal planar molecule. And these electrons plus the electronegativity difference with the nitrogen being at 3 versus 2 will pull those electrons, that charge, up. So here in the electronegativity tug of war, we see that our nitrogen and our lone electron pair wins, and there is a separation of charge. Notice also that this lone electron pair kind of wrecks our symmetry, because we still have to contend with that. The symmetry would be different if it were trigonal planar, but because it's pyramidal and we have this difference in geometry, we don't have the symmetry we saw before. So this molecule is polar, and what we find that at least in our class and in most cases, all trigonal pyramidal molecules will be polar because of the lone electron pair. And we'll see that that will play into another geometry in just a minute. Welcome to Polarity of Molecules Part 7, the bent or angular geometry. This geometry is very similar to linear. However, you notice the terminal atoms are bent out of the plane of the central atom. What causes that bend? You can probably guess based on the trigonal pyramidal. There are 2, in this case, instead of just 1, 2 pairs of lone electrons. That is, two electron pairs that do not bond with any other atom, but they're still here. And they do exert a force on the terminal atoms, pushing them out of the plane of the central atom, creating this bent geometry. How does this affect our polarity, or does it affect the polarity? This bent shape, a good example of it would be water, H2O, and I'm not going to give the technical name for it. We know it as water. The two terminal atoms are the hydrogens with the 2.1 electronegativity, and they are bent down and out of the plane with the oxygen, which has an electronegativity of 3.5. And again, we see with those electrons on the top and the high electronegativity, the electron kind of flow is going up towards the top here. So again, if we look at that electronegativity tug of war, it's going to be angled up towards the oxygen and the lone electron pairs, creating a separation of charge. Partial negative here on the top, partial positive on the bottom. Water is very polar. In fact, it's almost like the poster child of polar molecules. So it does create a difference. These two lone electron pairs create that bent geometry. And if you notice here, because of also, again, the lack of symmetry, all of our bent molecules will be polar. Welcome to Polarity of Molecules, Part 8. You finally reached the end of this video. Congratulations. Tetrahedral is the last geometry we will look at. It has a central atom with 4 atoms bonded all the way around it. Remember, these atoms are equally spaced from one another, even though it looks like most of the molecules are on the bottom. Remember, it's in 3 dimensions. So if you have trouble with this, come by my office and look at the models. That will make it a lot clearer. It's kind of hard to represent sometimes in 2 dimensions, but we'll do our best. Okay, I have 2 examples of tetrahedral molecules, and they're closely related. The first one is carbon tetrachloride. This is one central carbon atom with 4 chlorine atoms spaced equally around the central atom. Notice all the chlorines have the same electronegativity, so they'll have the same electron pull. And again, with the symmetry, all of the poles basically cancel each other out. That is, this pole will cancel out this one, and this one. So in the electron tug of war, or the electronegativity tug of war, nobody wins. There's no separation of charge. And again, this can be hard to see on a blackboard or on a whiteboard. It's a lot easier if you come by the office or get me in class, and I can show you the models, and it's much easier to see in 3 dimensions. So all of these poles cancel each other out, and because there's no separation of charge, carbon tetrachloride is nonpolar. So what happens, again, I'm going to play God, and I'm going to create a new molecule by taking off one of the chlorines, and I'm going to put on there instead a hydrogen, which has a much different electronegativity, as we see it with our drawing up here. So I have a hydrogen here, and then 3 chlorines bonded as my terminal atoms. So how does this change my polarity, or does it? Well, in fact, it does, because now all of the electrons are basically being drawn down. In this case, it looks like the bottom of the molecule, but remember, they can always rotate around, so it doesn't matter the orientation. So I have a partial negative charge down here, a partial positive charge up around my hydrogen. So now what was my carbon tetrachloride nonpolar is now trichloromethane, which is very polar. So we have a difference in polarity just by changing one atom. What does this do? That change of the atom basically messes up the symmetry. So here's where another place where symmetry plays a big part in whether a molecule is polar or not. So this wraps up the polarity of the molecules. You'll see that many geometries have both polar and nonpolar examples, but 2 of them, the bent and the trigonal pyramidal, have only polar examples here. So hopefully this will help you with your understanding of polarity of molecules. Thank you.